This is the fifth part in our Introduction to Pseudospectral Methods. In previous parts, we described and discussed Fourier pseudospectral methods. And here we again have a linear combination of basis functions, but we're going to use Chebyshev polynomials of the first kind as our basis functions. So these are convenient when we have non-periodic domains, and the domain of interest will vary from -1 to 1, although we can use arbitrary domains from A to B and map them to -1 to 1 using a simple linear transformation that's given here with these equations. So the first 7 Chebyshev polynomials are listed on the left and plotted on the right. T0 is just the constant 1, T1 is the function x, T2 is 2x squared minus 1, etc. And these have a really strong sinusoidal character, and you can also see that they vary and are bounded by from -1 to 1. And this is because they're directly defined in terms of the cosine function, which of course varies from -1 to 1 and has this cosinusoidal behavior. So the Chebyshev polynomials are really simply defined. The nth Tn of cosine theta is simply cosine of n theta. And we'd like to see how this relationship here, how this definition can be used to generate these Chebyshev polynomials. So first we'll just define x to be cosine theta, and this just gives us a variable transformation from theta to x, and literally just projects points on the unit circle defined by angle theta onto the x-axis. So from the definition, when n is 0, we have cosine 0, and that's just 1. When n is 1, we have cosine theta, which is just x. When n is 2 or 3, etc., we have a recurrence relation where we define t3 to be 2x t2 minus t1, and so forth. So t3 will be 2x times t1, which is 2x squared, minus t0, 2x squared minus 1. For t3, we have 2x t2 minus x t1. So 2x t2 will be 4x cubed minus 2x minus another x gives us 4x cubed minus 3x, etc. So we can show explicitly for n is 2 in this formula if we use Euler's identity. So in that case, e to the I theta quantity to the power n is the same as e to the I n theta, and and this is going to give us cosine theta plus I sine theta to the n is the same as bringing the n argument inside because of this power definition. We can solve this for cosine n theta, which we want cosine n theta for the trig polynomial. And if we do that, then we have cosine n theta is equal to e to the I n theta minus this imaginary component. And we can then use Euler's identity here to the n, and we're going to have this relationship. So if n is 2, we can expand this quantity, square it, and if we collect the imaginary components here, which will cancel because the Chebyshev polynomial is real, then using this identity cosine squared theta plus sine squared theta equals 1, we can replace this sine squared theta with, write it in terms of cosine squared theta, and then we get this quantity here, which is just the t2 that came from our recurrence relationship. For higher values of n, we can do the same thing, but now we're going to expand this power using binomial expansion. And I've listed the imaginary terms in red here, and the imaginary terms, of course, are all going to cancel because the polynomial is real, and the imaginary terms are those with odd powers. So if we use y equals sine theta, so x is cosine theta and y is sine theta for convenience, then we just have x plus iy to the n, and that's what we're going to expand. And then if you analyze this for different values of n, you can show without too much effort that you end up with this relationship given. And in practice, to evaluate these efficient methods for computing these are available. Okay, so let's look at the trigonometric relationship a little bit more carefully. So we've defined x equals cosine theta, where theta is the projection on the unit circle to the x-axis. Now, cosine theta is an even function, so we're primarily interested in theta varying from 0 to pi, since negative values give the same cosine. So if we go positive, we get the same as if we have negative angle to the same magnitude. As theta varies from 0 to pi, n theta will vary from 0 to n pi. So from 0 to pi, we get half a wave, half a cosine wave. From 0 to 2 pi, we get a full cosine wave. From 0 to 3 pi, we get 1.5 cosine waves, etc. And so if we look at the unit circle, then as theta varies from 0 to pi, using subsequent increments, we get this projection onto the x-axis, and we have a clustering of the grid points, with closer clustering near the boundaries and further clustering on the edges. The actual value of the polynomial is cosine of n theta. So as we go from 0 to pi, we're going to have n, effectively n over 2 full waves that are going to vary on this circle. So if we were to color this, -1 is blue and +1 is red, then you're going to have oscillations between blue and red along this line. You can't see the shape of the curve because it's out of plane, but we can tip the plane. So if we plot this quantity, then as we go around the unit circle from 0 to pi, then the value of the function is cosine n theta. So theta goes from 0 to pi, and cosine of n theta oscillates as shown. So if we make n equal 0, we just get a constant 1. If we make n be 1, then we get half a wave. We effectively get a half of a cosine wave. If we make n is 2, then we get a full cosine wave. It goes down to a minimum and then back up to where it started. When n is 3, we get 1.5. N is 4, we get 2 cosine waves, etc., that fill in between this theta 0 to pi. And those effectively circle around this unit circle, the magnitude. Now we're going to project the theta value for a given theta. It gets projected onto the x-axis, and that's the same as projecting this curve onto this green plane. So if we look at the projection, we actually have an image of what those Chebyshev polynomials look like. So we have kind of two things happening. One is the projection of the angle theta onto the x-axis, so the location of where this blue curve projects onto the green plane. And then we also have the up and down oscillatory motion, which is the value of the polynomial. So you have t of x and then what it equals. So you have you have the x location, and then the which is where the points lie, and then the magnitude is the 2x squared minus 1. And so we can see really clearly, hopefully, how these relate to the geometric picture and how they relate to the cosine functions. So it's worth spending a little bit of time. You can play with the slider to try to understand really clearly what this geometry looks like, and also how these relate to the mathematics that are given here. I'm not giving really formal proofs, for example. I haven't given a proof of this recurrence relation, just kind of showing that it's there, and also some of these relationships that you can derive to get a little better feeling for what these polynomials are. Okay, finally, let's just look at the roots and the extrema. So there's, for when big N, given big N, so say N is 6 or whatever, Tn is the, there would be N roots for this polynomial. So if we go from N is 0 to N minus 1, then Tn minus 1 will have N minus 1 roots. And those roots are located at theta j are pi over n j plus a half. So that gives effectively uniformly spaced theta values, except we don't start at 0, we start a little bit higher up. So j plus a half, and then they're uniformly spaced. That's where the roots live. And so that's plotted here, as shown here in this figure. And then the x values are just cosine of the thetas. So that's where the roots of that polynomial happen to live. The extrema, there's n plus 1 extrema of polynomial Tn. So if we have n is 0, then we'll have one sort of extrema value. If n is 1, we have two extrema, one at minus 1 and one at 1. If we have 2, we have 3 extrema, here at point minus 1, 0.0, 0.1, etc. So you can see here when we have 8, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 extrema, and the locations here are 1, and then as projected onto the x-axis. Okay. Now, when using pseudospectral methods, we need to pick a grid for our locations. So in Fourier methods, we used a uniform grid. In Chebyshev methods, we're going to use a non-uniform grid, and the most popular grids to choose are either the extrema grid or the roots grid. And we'll look in the next part, we'll look at Chebyshev interpolation to kind of demonstrate why you want to use those grid points, basically to avoid the Runge phenomena. Okay, also when using these to solve partial differential equations, it's convenient to use the extrema grid because it includes minus 1 and 1, which allows us to directly treat our boundary conditions. So that's kind of the method, the grid of choice when using those. But we'll show all of our examples using both the roots grid and the extrema grid. Okay, so that concludes this part, and then we'll discuss Chebyshev interpolation in the next part.